So far, we have introduced how to do matrix factorization to solve the collaborative filtering problem in recommender systems. We haven't studied how to develop the scalable versions for big data, for millions or billions of users and items. So let's look at how Spark do scalable collaborative filtering. There are three key considerations in scalable machine learning. The first one is that we prefer to have linear computation and storage. This will lead to low cost in computation. That means in terms of time cost and space cost. Linear means the computation and storage will be linear in terms of the number of samples and the dimensionality of each sample. And secondly, we need to be able to perform parallel and in-memory computation with many workers work together and try to reduce the need to access lower level memories. This is provided by the Spark framework. Finally, we also need to minimize the network communication overhead. This is because when you have many workers working together, it's not necessary that the more, the better. If you are not careful, it can be, when you have more workers, it can be slower because there's an overhead in parallelization. Right? So you need to communicate with different workers. Right? That is just like when you have, we have 100 students working on just one project, then there will be, if we are not managing it carefully, there can be lots of communications, right? Many people didn't talk to each other, and this is not free, it's not instant, it will have an overhead. Therefore, in Spark, ALS, the alternating least squares, is implemented with a blocked implementation. So in this blocked implementation, Spark will group users and items into blocks. And they will group them into blocks. But how to do it, right? How to group items and users into blocks to reduce the communication between different blocks. And so therefore, the objective of blocking is to reduce the communication. We want to reduce the communication so that we can only send just one copy of each user vector, right? The user factors to each item block on each iteration. Right? And only for the item block that need the user's feature vector, right? So if the items block do not need the user feature vector, then we don't need to send the user feature vector, right? So in this way, the communication will be efficient, right? So this is a way to reduce unnecessary communications. And to do this, right? To do this, we need to pre-compute some information, right? So therefore, Spark will pre-compute some information. You need to compute the outlinks for each user, right? So that is which blocks of the items it will contribute to. And so that is basically which items that the users have rated. And so therefore, there'll be some computation for the outlinks. And it will also pre-compute the in-links for each item. That is, which of the feature vectors it will receive from each user block. It depends on, right? So that is what are the users has rated those items. As you need to compute these links, and when they have the blocks, the links, right? So between different blocks should be minimized. That should be minimized. But this, you don't need to worry about this, right? Because this is implemented by Spark, right? But it's good to know how they do that. And in Spark, you also have the capability to do implicit feedback modeling. Right? So you have an option to do implicit feedback modeling. Implicit feedback is those kind of implicit ratings we mentioned before, like number of views, clicks, purchases, likes, shares, right? So those kind of implicit ratings, right? So here we can define the rating as strengths in the observations of user actions, right? So for example, the number of clicks or the view durations, right? So how long the user have viewed a video. And this can indicate the confidence level in the observed user preference. Right? So here we use the word preference. And to model the implicit feedback, we can construct a preference matrix P. The simplest way is to let its entry equal to 1 if R is greater than 0 and 0 if R is 0. Right? That means if there's a clicks, no matter how many, you have a 1, right? So for that interaction, right? So and 0 otherwise. And then we do a factorization on P to learn the latent factors to predict the preference of a user for an item, right? So this is the approach taken in a paper from ICDM 0.8, right, 2008. So let us take a look at the APIs of ALS in Spark. So there's we can specify the number of user blocks and number of item blocks, right? So this will be the number of blocks, user and items will be partitioned into, right, to parallelize the computation. And there will also be a rank, right? So a rank parameter. This is the number of latent factors in the model. Right? So that's a default to 10. So the rank is the K in our previous slide, right? That is the K in our previous slide. That is a dimensionality for each of the factors. And regularization parameter is a lambda in our equation, in our objective function, which is a regularization parameter. And there's a Boolean parameter called implicit preference. This is to indicate whether to use the explicit feedback or use implicit feedback. And alpha is a baseline confidence for implicit feedback. And non-negative is to constrain the ratings to be non-negative, right? Because that is typically, right, so in real world, the ratings are typically a non-negative number. And another is a cold start strategy, right? Cold start strategy have two options. One is drop. When we specify the strategy as drop, we will drop any rows in the data frame of predictions contains not a value, right? Not a number, right? Not a number means missing. And if the default is none, right? Is none. It will assign none, right, to a user or item that is not present, that is missing. In the latest version, right, so there's also a block size that you can specify the size of the user product blocks in the blocked implementation of ALS to reduce the communication, right? So these are the APIs that you make use. You can set many different options, right? So this is a code, right? So the code is in Scala, and if you go there, you can see the code, right? How the code is written, right? So for the ALS, right? So this is ALS. It's a train method. You can see all the parameters over here defined, and all the implementations, right? The user in block, user out block, right? That is the in link and out link and different things, right? So we have block ratings and so on, right? So, right. So that is brief look of the key API for the ALS method. So as we have seen just now, right? So in Spark machine learning, right? So also when we are using PySpark, you still are running Scala code, right? We are still running Scala code, right? So the ALS is implemented using Scala, right? So therefore the source code is over here. You can click this link to take a look at the Scala code for ALS. It's a very lengthy implementation, right? It has 1,000, almost 2,000, 1,800 lines. And you can also consult the documentation about collaborative filtering. And there's also a movie tutorial provided by Databricks. And Databricks is a company founded by the creators of Apache Spark, right? So I encourage you to look at their packages from their GitHub page. And they also provide a Databricks community edition, which is a free computing cluster computing platform that you can get 15 gigabytes of memory for free, right? So, and if you want more, you need to pay. But you have 15 gigabytes of memory free for this Databricks community edition, right? You can use your email to sign up. Okay, so that finish this scalable matrix factorization for collaborative filtering, right? So in recommender systems, there are three key references, right? So the first one is the paper on matrix, what we have covered by the matrix factorization for recommender system, right? So this is a paper published more than 10 years ago, right? So from the industry, right? So from industry, Yahoo and AT&T. And for the implicit feedback, right? So method implemented in Spark, it's also published from the same group, right? From the same group with a different first author, but two of the previous authors, right? So published in 2008 in the data mining conference. And there's also a book, right? So the topic is a huge topic, right? It's also with a highly commercial interest, right? So there's a textbook on recommender system, right? So if you're interested, you can buy it, right? So I think you need to pay for that textbook. Okay, so that finish this session 3, right? Session 3. Then the next video will be on the lab.